Good morning. This is Dr. Maheshwaran. Today we are going to see Unit 4 Scattering of Light from Physical Optics paper. Scattering of light. This is a physical phenomenon when a light passes through a medium and due to the particles present in the medium, the light is forced to deviate from its path or a change in energy or in both. We call scattering of light. There is two types of scattering. One is elastic scattering, in which there won't be any change in the energy of the photons. The other type is inelastic scattering, in which there is a change in energy of the photon. Light scatters in various ways, depends upon the medium and the particles present in the medium, out of which there are few mechanisms explains these various scatterings. Example: Rayleigh, Tyndall, Raman, Thomson, and Compton scattering. Rayleigh scattering: when a light enters into a medium where the molecules or the particles are very smaller than the wavelength, this type of scattering will occur. This is actually an elastic scattering, and according to Rayleigh scattering, the intensity of the scattering depends upon inversely to the fourth power of the wavelength. That is, higher wavelength scatters very less, and the lower wavelength of light will scatters high. This is a beautiful concept, okay, which explains why the sky appears blue in the day and red or orange in the sunrise and sunset. Now let us see why the sky appears blue in the daytime and in the sunrise and sunset why the color is changing. Let us now consider in the air. We are just standing here, okay, and this is the atmosphere. Just think of this. During the sunrise, the light ray has to travel in a longer distance to reach our eye. Due to this, all the colors will scatter and goes out. So finally, the red color will reach our eye. So in the visible region, when compared to just violet, indigo, blue, green, yellow, orange, red, so red is having higher wavelength when compared to the other colors. So the red color will scatters very less when compared to other colors. So what will happen during the sunrise? The distance of the sunlight reaching our eye is very high, so that all the other colors will scatters in the space and only the red color is reaching our eye. So it looks like a sky is reddish orange. In the same manner, in the sunset also. During the daytime, the distance of the sun and our horizon is very less when compared to the morning and evening. So the distance is less. So the blue color will scatters more than the other colors. So the remaining colors will reach our eye. So the sky appears blue. Tyndall effect. In 19th century, John Tyndall discovered this effect. When a light passes through a colloidal solution or a solution which contains a fine suspension, that is, the particle size comes around 10 to 1000 nanometer. So the light will scatter due to these colloidal particles. That is, the path of the light is disturbed by these colloidal particles. And this comes under elastic scattering. The intensity depends upon the frequency of the light and the density of the particles in the solution, that is, concentration of the solution. So in this, you can see uh, two beakers. The first beaker contains a true solution, that is, the solute dispersed particles are very fine. It is a true solution. And the second beaker contains a colloidal solution. The same light passes. In the first beaker, you can't see the path of the light inside the solution. But in the second beaker, you can see the path of the light. That is, the light is scattering because of these colloidal particles. This effect was discovered by John Tyndall. So, using this idea, you can see here the second picture. When a light passes through a true solution, the path won't be visible. In the colloidal solution, the path will be visible clearly, and in the fine suspension solution, the path as well as the particles will be visible. All this because the light is scattered by these particles. Raman scattering. This scattering was first discovered by Sir C.V. Raman in 1928. This is an inelastic process. That is, when a light interact with the molecules which are having a vibrational energies, there is an exchange of energy between the molecules and the photons. So due to that, the emitted photons is having frequencies, that is energies other than the incident photons. There is a three possibilities. First thing, the emitted photon will have the same energy as the incident photon. We call it a Rayleigh scattering, a elastic scattering. Along with this, there is a possibility when these photons interact with the molecules and contributes an energy for its vibration. So see here, so the vibrational energy will change, and while returning back, it will emit an energy of a photon which is lesser when compared to an incident photon. We call this as a Stokes scattering. It's an inelastic process. That is, the energy is changing. Here, the wavelength will increase, but the energy and frequency of the emitted photon will be less when compared to the incident photon. In the same manner, you can see in the next possibility, when a molecule absorbs a photon, it will go to a next vibrational level. While returning back, it will emit a higher energy or a lower wavelength. We call this as an anti-Stokes scattering. So this Stokes and anti-Stokes are inelastic in nature, that in both the cases the energy is changing. As explained in the previous slide, this is just a brief about that. So when a monochromatic light passes through a material, it will produce a frequency addition to the original one. This phenomenon is known as Raman effect. So the emitted photons may have higher frequencies or lower frequency. The lower frequency light is termed as Stokes scattering or Stokes line, while the higher frequency is called anti-Stokes line. And there is a photon will emitted with the same frequency of the incident light. This is called Rayleigh line. More detail about this Stokes and anti-Stokes lines. In Stokes line, the photon loses energy to the molecule, so the scattered photon has a lower energy, longer wavelength. This is more intense than anti-Stokes lines. There is more number of Stokes lines will be observed. Anti-Stokes line, the photon gain energy from the molecules, so the scattered photon have higher energy, shorter wavelength, we call anti-Stokes line. This is less intense due to the fewer excited molecules, that is less number of excited molecules. The very important applications of a Raman scattering. We can identify molecular composition based on its vibrational and rotational energy. That is, based on their vibrational energy levels, it will absorb a light, incident photons. Detecting that, we can calculate the molecular composition and pollutants. We can study the crystal structures also. Overall, of a scattering of light, actually scattering is a physical phenomenon. It explains the optical property change. In this, the Rayleigh scattering explains why the sky is blue. Tyndall effect shows the path of the light in a colloidal solution. And using a Raman scattering, we can get more information about the molecules present in the medium. Thank you.